Flipped classroom video for Maths AS Unit 1, Laws of Indices. So we'll look at the basic laws of indices. You've looked at these in GCSE, but we'll just run through them anyway. So, multiplying. When multiplying powers of the same number or variable, we can add the powers. So, if we look at an example, if we had x cubed times x squared, then that means we've got x times x times x times x times x. The first three are the x cubed and the final two are the x squared. That means we have x to the 3 plus 2 and therefore x to the power of 5. Dividing. When we're dividing powers of the same number or variable, we can subtract the indices. So as an example, we've got x to the power of 5 over x squared. That means we have x times x times x times x times x for the numerator and x times x the denominator. So we've got 5 on the top and 2 on the bottom, so the 2 on the bottom cancel with 2 of the ones on the top, leaving the 3, which is why we can say this is x to the 5 minus 2, and therefore x cubed. Power of a power. When we're finding the power of a power, we can multiply the powers. So as an example, we have alpha squared all cubed, and that means we have alpha squared times alpha squared times alpha squared, because we're cubing it. That means we have alpha to the power of 2 plus 2 plus 2, or another way of looking at it is 3 lots of 2. So that gives us alpha to the power of 6. So we get some general rules, and notice that so far we've only established these or shown these for positive whole number powers. And that's what m, n, funny e, funny n, slash, squiggle, brackets, 0 means. So what that means is the numbers m and n are members of, that's that sort of Greek e, n is the natural numbers, and the slash means without, and the curly bracket with a 0 on means without the number 0. So what it's saying is that m and n are natural numbers, which means the numbers 0, 1, 2, 3 and so on, but without 0. So that's a mathematical way, if you like, of saying m and n are positive whole numbers. The reason for that is that we've only shown it using methods that can be shown using whole numbers. For the division one, notice that we've shown a division with the power on the top being greater than the power on the bottom. So really we've only shown that when we divide we can subtract the powers for natural numbers where the top is greater than the bottom. The power on the top rather is greater than the one on the bottom. And we've also shown that c to the power of n to the power of n is c to the power of m times n for whole numbers. So we need to think about zero and negative powers. And for the 0 power, we can use what we've discovered about division of powers to give meaning to y to the power of 0. And in a sense, we are extending the way we deal with positive whole number powers by making the rules make sense as we extend into other numbers like 0. So we know that any number divided by itself is equal to 1, so we can say y cubed divided by y cubed is 1. But if we use our previous rule and say, well, we want it to work in other situations, then we can say that y cubed divided by y cubed is y to the 3 minus 3, and that is equal to y to the power of 0. And therefore, because all those things are equal, we can say that that is equal to 1. And notice here, we've relied upon division. We can't divide by 0, so is it true to say that 0 to the power of 0 is equal to 1? And I'll leave that as something for you to investigate. For negative powers, we can also use, as we have done, what we've discovered about division to give meaning to negative powers. So, if we had y cubed over y to the power of 5, that would be y times y times y over y times y times y times y times y. We cancel 3 of the y's, and we're left with 1 over y squared. Now, if we use our previous rule, then we'd have y cubed over y to the power of 5 is equal to y to the 3 minus 5, which is equal to y to the minus 2. And so we can define y to the minus 2 as equal to 1 over y squared. More generally, we can say that y to the power of minus n is equal to 1 over y to the power of n. And if we cross multiply, that allows us to say that y to the power of n is equal to 1 over y to the power of minus n. So now we get general rules that a to the power of 0 is 1 as long as a is not equal to 0. B to the m divided by b to the n is equal to b to the m minus n, and that's now for all m and n in Z, and Z is the set of integers, so that's positive and negative whole numbers. And we can say that b to the minus n is equal to 1 over b to the n. Okay, now we move on to fractional powers and roots. So what is k to the power of half? Well, what we do is we investigate this and see what happens if we use our previous rules. So we want our rules to work for fractions, so we use them to make them work for fractions. So if we have k to the power of a half times k to the power of a half, then using our previous rule, extending our previous rule, then we can say that that's equal to k to the half plus a half, and that is equal to k to the power of 1. Now we can also say, of course, that k to the power of half times k to the power of a half is k to the power of a half squared, and we can also say k to the power of 1 is just k, and so we get k to the power of a half squared is equal to k. That means that k to the power of a half must be the square root of k by square rooting both sides. What is k to the power of a third? Well, we can extend what we've just done. We can say that k to the power of a third times k to the power of a third times k to the power of a third is equal to k to the power of 1. That means k to the power of a third cubed is equal to k, and that means that k to the power of a third is the cube root of k, because we can cube root both sides of the line above. And that leads us on to what is k to the power of 1 over n, and by extension we can see that k to the power of 1 over n is the nth root of k. We also want to be able to deal with fractions that don't have 1 on the top. So what is k to the power of m minus? So what is k to the power of m over n? And again, by extending from previous rules, we see that k to the power of m over n is equal to k to the power of 1 over n to the power of m. So that's using the power rule sort of backwards, as it were. And we know that k to the power of 1 over n is the nth root of k, and so we can express k to the power of m over n as the nth power of k to the power of m. We could also do it the other way round. We can say that k to the m over n is equal to k to the m, all to the power of 1 over n, and therefore it's equal to the nth root of k to the power of m. And now our general rules look like this. We have root a is a to the power of a half, the nth root of a is a to the power of 1 over n, b to the power of m over n is the nth root of b to the m, or the nth root of b all to the power of m, and we can also say that c to the minus m over n is equal to 1 over c to the power of m over n. And we can also say that c to the power of minus m over n is equal to 1 over c to the power of m over n. And the reason we can now say that is that we've successfully extended our rules to fractions, and therefore we can apply them to that rule as well. Okay, now that's all very sort of abstract, but you had come across that before and used them, so hopefully it's not too much of a shock. But now we'll look at some examples. So here we've got 16p to the power of 8 to the power of 3/4, and there are different ways of tackling these questions, so this isn't the only way to do it, but it's one way to do it. And very often with fractions, the best thing to do is to split it into the bottom of the fraction, which is going to give you the root, and the top of the fraction is going to give you the power. So we now have the fourth root of 16p to the power of 8. That 8 looks a bit big there, it should have been a bit more littling up, but it is p to the power of 8, and we know that from the previous, from the typed question. And then all of that is to the power of 3, or cubed. Okay, now we can also split that up, so that's the fourth root of 16 times p to the 8 over 4, because it's a root, we're dividing by the root, and that gives us 2p squared inside the bracket, which then has to be cubed, so that means we have 2 cubed, which is 8, and p squared cubed, we use the multiplying rule for powers of powers, and that gives us p to the power of 6. Next example, we have 7 over 2 to the power of minus 2. And you can do these in one go once you've got used to these or you're adept at them, but it's a good idea to split it up. So what I've done is first of all dealt with the minus, which essentially flips the fraction upside down, leaving us with just squared, and then we have to square the top and the bottom. So that's 2 squared is 4 and 7 squared is 49, so 7 over 2 to the minus 2 is equal to 4 over 49. Next example, we've got 64 over 27 to the minus 2 over 3, and so again first of all we deal with the minus by flipping the fraction up, so we have 27 over 64 to the power of plus 2 over 3. Then we're going to deal with the root first and then the power. So we have the cube root of 27 over 64, and we can cube root the top and cube root the bottom. Cube root of 27 is 3, cube root of 64 is 4, so that gives us 3/4, which still needs to be squared, and we square the 3 to get 9 and the 4 to get 16, so we end up with 9/16. You'll also have to deal with rather more tricky algebraic sort of things, and this one, when you've got lots and lots of things, it's a good idea to write everything out, because cancelling can save you a lot of bother. So first of all we deal with that first bracket, 8p to the 4 times q cubed. Well, because everything's cubed, the 8 has to be cubed, so I write that as 8 times 8 times 8. The p to the 4 is cubed, so I use the multiplying rule, so that's 4 3s are 12, so that's p to the 12. And then the q is just cubed, so q cubed. We still have to times that by 3q. Then we're going to deal with the 2p squared q cubed. So the 2 is cubed, so we get 2 times 2 times 2. The p squared is cubed, so that's 2 times 3 by the multiplying rule, so that's p to the 6, and again we have just a q there, so that's q cubed. And then we times that by what's left, which is 4 times p to the 4 times q to the 10. And now you can see the benefit of writing stuff out, because we can do some cancelling. The first thing we can do is the first 8 there, I'm going to cancel with the 2 at the beginning and the 4 that's further down. So 2 4s on the bottom are 8, cancel that with the 8. I'm then going to cancel the next 8 with 2 of the 2's on the bottom, so the 2 times 2 on the bottom is 4. 8 divided by 4 is 2, so that still leaves us with 2 on the top. Now the letters, we could do some cancelling of powers, so for example p to the 12 over p to the 6, we could cross the 12 out and put 6 and cross the 6 out, p to the 6 all together, and you might want to do that. I've chosen to tidy up from where we are, so on the top we've got 48, which comes from 2 times 8 times 3 towards the end of the line there, which is 48. For p I've got p to the 12, and for q I've got q cubed times q, which is q to the power of 4. On the bottom all the numbers have been cancelled, but I've got p to the 6 times p to the 4, which is p to the 10, and I've got q cubed times q to the 10, which is q to the 13. And now I can do the subtraction of when we're dividing powers, so that gives me 48p squared on the top and q to the 9 on the bottom. The 2 comes from the 12, take away 10, and the 9 comes from 13, take away 4. And if you were required to write it without a fraction, then we could convert the q to q to the power of minus 9 rather, and that would give us 48p squared q to the minus 9. And you'll probably do loads of practice with these sort of questions, and it's good to get very fluent with them if you can.